Okay, well, right now is something um, a little different, something I haven't done before, and hopefully won't do again, if I'm being honest. I have some more videos that I was going to record, very standard. I have another quantum mechanics video and TensorFlow quantum video all lined up. So don't worry, content like that will be coming, but I just wanted to sort of address something I saw online, basically regarding quantum computing. Now, I see a lot of not great takes regarding quantum computing. In fact, I would say probably the majority of takes I see on the internet regarding quantum computing are pretty bad. Um, and I don't respond to any of them because, no point in doing it. But I did see most of the time it's coming from like investors or non-tech people who are, just insanely overselling quantum computing is basically like what I see a lot of online. So I don't want to address them. You're never, I mean, those people have sort of monetary incentives to act the way they're acting. So you're not going to like change their minds because then you don't have the money to change their minds. But this video, I'll be honest, I didn't watch the video. I just read the transcript here. This video was published entitled "The Quantum Hype Bubble is About to Burst," and it's from a very popular YouTuber who I had never heard of before, in all honesty. Um, and because it comes from the scientific perspective, and it has hundreds of thousands of views, so lots of people are watching it, and it's presented as, it's not, some rando investor who you shouldn't you should trust as far as you can throw, right? It is a real scientifically literate person, and they are scientifically literate. um, there's sort of more trust there. But I do think this is not all bad, but I think there's some common sort of problems I see here that I sort of want to address. And I don't disagree with all of it. And right off the bat, let me just say, at face value, quantum winter is coming and the quantum hype bubble is about to burst are both things that I agree with, and I think are, from a normative perspective, maybe good things. As a funny anecdote, when I was interviewing for companies right after I graduated college, or I guess during the last month of college, one of the companies I applied, well, I applied to many quantum startups, but one of them, in the final round, like interview, I presented to the whole company like about myself and other stuff. And one of the questions they had me present about was something like, what do you think quantum computing needs, like as a field? What's missing or something? And my answer to that was a quantum winter. Now it's funny to go into a startup and say, who is very reliant, right, on funding, and say the thing that quantum computing needs is less funding, basically. But I didn't mean it in any monetary sense. I'm not concerned with that. I'm more saying, like, I think there's too much work of not enough quality going on. I have the same complaint with machine learning, if I'm being honest. But so I want to say out the bat, I don't buy into the quantum hype. I have a lot of skepticisms that I won't even be addressing here. But um, I just want to preface that by saying, I agree that I don't know if a quantum winter is coming, but certainly some quantum snowfalls are coming, and I think that'll be a good thing for the field as a whole. The first thing I want to notice too, that a winter's coming does isn't long term bad or a good thing. AI has gone through multiple winters, and now it's, king of the world right now. It didn't do, I mean, it did a lot of interesting stuff pre 2012, but since then it's done crazy cool things like Superhuman Go. And well, that's really I'm biased towards RL, but that's one of the cool things it's done. So AlphaFold, that was pretty cool. So stuff like that. And that was after, 3 or 4, however many winters since the 50s. So, sometimes patience is valuable. But without further ado, let's get into this video slash transcript, and go through sort of section by section what I think is right. And they do get a lot of things right. The person who made this video. But I do think they also misrepresent or get certain things wrong. And I don't know, I think I'm not familiar with them. Maybe they're sort of quantum adjacent. So, staying up to date in quantum computing is really hard. I acknowledge that. So, yeah, let's get into it. Yeah, you can watch the video. Of course, everything talk about will be linked below. So um, the first thing I want to address is basically, but so much of the quantum hype, if so much of quantum computing is hype, then why are Google and IBM pouring, etc.? Microsoft is also up there, pouring money into it. I don't think this is really a fair characterization. Now, I don't know, the details of these companies' finances, but looking at Google, if you look, on LinkedIn and on the papers they're publishing, there's, 100 people or so on those papers. They have like one office, I think. And their like summer symposium or whatever I watched. Um, they only have a few chips. I can't imagine they're putting more than $40 million into this. And so that's not like, I mean, Google's worth like trillions of dollars, right? They're like the top five most valuable companies in the world. Like, that's not a lot of money. I wouldn't categorize that as pouring money into it. I would say certain AI endeavors, like I'm pretty sure DeepMind operates at like the last figures I saw was like a $400 million loss. Like that's pouring money into something. So I sort of disagree with this characterization that they're pouring money into it when I think that, it's really, considering the scale of these companies, not that big of an investment. Um, so then moving on, she talks about this rule of thumb: the fewer headlines they make, the more promising they are. I have no idea where this comes from. I don't know if I agree with it or not. Quantum metrology, which is like measurement stuff. Um, you never read anything about this, which is really weird to say because it's like a specific application research area. You're never going to hear anything about this because it doesn't have as wide commercial relevance. And it's like, okay, you don't hear anything about, a billion group mathematics for quantum algorithms, which is, there's a lot of stuff in the super polynomial speedups that have to do with like these a billion groups. You never read anything about that, but that's because it's a very, specific research area. Like that doesn't mean you never read anything about, hardware efficient ansatz. Like that doesn't mean it's good or bad. That just means it's probably niche. And won't actually have widespread commercial applications. So that, I mean, I don't really know if that's a good rule of thumb. But and then they talk about the quantum internet, which is, I have no idea. I don't know anything about the quantum internet. I don't know if anyone needs it. I don't know. So I'll accept that. Nuclear fusion, I'm still hopeful for. But this is where I agree. A lot of physicists, me included, and myself being now me, Owen, who is speaking, have warned that quantum computing is being oversold. And I absolutely agree. I think that quantum computing is overhyped. I think that's kind of the common sense. I think you'll have a hard time meeting anybody who's at all scientific in the quantum computing world who doesn't say quantum computing is overhyped. I would be amazed if there was sort of a reputable scientist who would take that stance. Especially for near term, I should say. I don't like fault tolerance is different. I should focus on near term. Like the current quantum computing is what we're talking about. And this is not going to change the world. I mean, that's an unquantifiable statement, right? Like getting up in the morning changes the world. Like the position of all the atoms in the world is different. Like everything changes the world in some capacity, like however small. Quantum metrology will change the world in its small little area. Like that's not like a quantifiable statement. So, I guess like, okay, whatever. Maybe it will, maybe it won't. But that's not like, I don't know. That's just a weird, phrasing. Then there's some startups. I don't know anything about multiverse or universal quantum. I don't know. There's just some jokes here. 6 reasons Liz Truss needs a quantum computer. I read this Medium article. It is pretty overhyped. Also funny because Liz Truss is now no longer the prime minister. But basically, it's crazy. They're like, quantum computing can help with inflation. I never heard that before. I don't think that's true. But yeah. So I agree with them. These startups often overhype what quantum computing can do. I will agree there. But here's another thing where there's sort of just blind statements made weather forecasts on a quantum computer are true. No one knows how to do it. No one knows if it's even possible. Well, if the world is in fact quantum mechanical, which a lot of evidence indicates that it's at least somewhat quantum mechanical, then weather is by definition a quantum mechanical phenomenon. So its system, like we approximate it in these nonlinear understandings. But if quantum mechanics is at all right, then weather is a quantum mechanical system, so it can be described within this physical theory. So I don't get that. Like either the assumption is that quantum mechanics is false, and that's an implicit assumption, or the assumption is, yeah, that's basically what they're saying. Is because either quantum mechanics is true and it can describe the universe, or it's false and it can't describe the universe. In which case, weather cannot be described by quantum mechanics. But it's just weird to say that, because I think the default assumption is that for now we are going to take quantum mechanics as true, in which case weather, all the molecular interactions going on there, subatomic and higher, are subject to quantum mechanical forces, and as such will obey that system and could be modeled. But anyway, moving on. It's quantum hype, obviously, yes, lots of hype. And this is where we're really starting to get into some disagreements. After creating, they talk about quantum advantage. Quantum advantage, therefore, can be interpreted as being when a problem-solving power can be applied to real-world issues, which make it much more interesting for investors. And she says, the author says, that's just wrong. Quantum advantage has been demonstrated. And this is where I agree and disagree, in the sense that quantum advantage is not a universally defined. Like if you talk to people in the field, not everyone has the same idea of what quantum advantage is. Some people will, myself included, will restrict quantum advantage to certain algorithms, right? Like Gaussian boson sampling. Some people, obviously, that's what she's describing here, is you're sampling some distribution faster than you could on a conventional computer, but it's not very useful. And I agree, I'm not saying Gaussian boson sampling is useful, but I think it's important to say that quantum advantage is not like universally defined too. Like the advantage with respect to what area, advantage with respect to power consumption, advantage with respect to speed. There's lots of things as we broaden our understanding of what quantum computing can be good for, that makes it so that advantage is not like such a static term. So that's just wrong, is not true. That's just wrong according to the definition that you're implicitly using might be true. Yeah, a lot of CEOs overhyped. That's what I said before, bigger than fire. I also, I don't actually think quantum computing fridges are not actually as terrible as you might think from the emission standpoint. This is a weird statement, since biomass burning is like really, like if you look at carbon emissions by fuel source, burning biomass, which is fire, is actually like a really inefficient in terms of like carbon emission source of power. So I'm not sure why this statement gets made. It will produce more carbon emissions when we probably won't have a ton of quantum computers. Each one of them doesn't actually take a ton of power, and fire is a notoriously carbon, emission heavy product. Like it doesn't make sense to me. This comment is all I'm saying. The next thing I want to say is that when they talk about the bubble will eventually burst, I guess I'll say this here, but it doesn't. This is like a weird concept too, because I agree that it's overhyped, but the concept of a bubble has a very different scale. So when I say bubble, you probably think of economic bubbles. You're going to think of the housing bubble of 2007, 2008. You're going to think of the dot-com bubble of 2000. Those are probably the things that come to your mind right off the top of your head, because those came to mind for me. And to give you a hint of the scale, right? Quantum computing last year, and once again, I'll put the sources for this, saw like $1 billion in investment from investors. At the dot-com bubble, you were seeing more than $30 billion per year, multiple years on end. And not only that, but that's in 2000 and $1990, right? So I don't know how much inflation has made that worth. Maybe that's like $40 billion now. So that scale was massively different. Additionally, when the housing bubble burst in the United States, net worth declined about $13 trillion. So these bubble, like when you say a bubble and your bubble is like $800 million, like that's a tiny little bubble. When we talk about, economic bubbles, we're talking about, oh yeah, the housing bubble was a bubble. Well, I should say the subprime mortgage bubble, whatever. The quantum computing bubble. Okay, they're both bubbles. One of them was trillions of dollars. One of them is a few $100 million. Like, it's important to have some concept of the scale as well. And when we say it's overinvested, let's also compare it to other emerging technologies. Look up fusion and machine learning. Machine learning, for example, in the first half of 2021 saw more than $20 billion of investment. So that's, 20 times more than quantum computing saw all of last year in the first half of a year. And that's just, I mean, I agree machine learning has more of a near term use case, but still, like, when people describe, like, oh my God, quantum computing is so overhyped, like, it's important to get some scale. Like, okay, it is overhyped, but it's not like that. Like, okay, $1 billion is a lot of money, but like, it's not that. It's not like some unconceivable amount of money, like the trillions that went into the housing bubble. So, I just think it's important to get some perspective there. Um, and winter is coming. I don't know if that's true, but maybe. So now this is an interesting part. So yeah, quantum computers. Yeah, we all know how they work. Um, so we need qubits, right? So qubits are hard to work with. Superconducting qubits, and this is weird. This is a common thing you'll see online. Superconducting qubits are used by IBM and Google. You have to cool them down a lot to get the superconducting effects. Um, you have to cool it to outer space. This is always something they say, which is a really weird, like, point of comparison, is that that's colder than outer space. Like, I've never been to outer space. I have no frame of mind on how cold outer space is, but you see it all the time in scientific communications. Like, such a meaningless comparison. Not like I live in outer space. I don't know how cold it is. Um, and even so, they decohere within, tens to hundreds of microseconds. And that's like, okay, both of those things are true, but that's neither of those things is like necessarily a weakness. Okay, they have to be cooled a lot. Like, so do supercomputers. Like, okay, they don't have to be cooled to the same temperature, but you still spend an unbelievable amount of energy cooling them. So it's just like, okay, it's not like you're gonna have one in your. There's not gonna be one in the garage. So why does that matter in some sense? Like, they're gonna be in specialized facilities. So, and like, who cares that they have to be cooled down? We know how to cool them down, so like, problem solved. And they decohere within tens of seconds. Well, yeah, but if you can do your gates really fast, as you can, if you look, you can see gates take tens to hundreds of nanoseconds. Like, okay, you can get hundreds to thousands of gates within that time. So like problem solved. Like, these are presented as problems when they're just like features of the hardware. Like, okay, we know how to deal with these problems. Ion traps, they only have to be cooled to a few, they put only in quotes, but like a few Kelvin above absolute zero is not that hard, like with modern technology to get to. Like, we can get to 20 millikelvin pretty easily as well, all things considered. And so it's weird that it's like, okay, that's really cold. Yeah, I would not want to go outside when it's 2 Kelvin, but like, it's not like that's scientifically hard to achieve. Yeah, they're longer and slower. That's true. That's just, yeah. And I don't know which approach is better. I don't know a lot about hardware. They're both equally bad. Cooling isn't always expensive and energy intensive. It's actually not. If you look at the supplementary information of Google's supremacy paper from 2019, you can see that cooling actually isn't that energy intensive. Like, when you consider, compare it to the supercomputers of today, which is, a fair comparison of what quantum computing would offer, and look at the power consumptions. Like, no, like, quantum computing does not take that much. Expensive. I don't know how expensive. You can look up how much cryogenics equipment is, but like, okay, it's not like I would go out and buy one on my own salary, but like, it's not it's not like it costs $1 billion. So I'm just saying it's a weird sort of statement. It requires a lot of equipment, like so do supercomputers, and it's difficult to scale. Well, everything's difficult to scale. I mean, that's true, but it's like this is just like a weird quantification. IBM is building, yeah, see that, and they're working to solve that problem too. They're building really big fridges. What do you know? Um, some qubits operate at room temperature. I don't know anything about nitrogen vacancy, but and I'm not sure about photonics. I've seen several companies doing photonics, so I'm not sure if these is like a different kind of photonics. I'm not going to say here, but I will say if the photonics that, for example, Xanadu is doing is photonics on a chip, which I have no idea if that's what they're doing, then a quantum computer does exist, and we know what the challenges are to squeezing, rates or whatever it's called is the big challenges. I don't know if we know how to overcome them, but like photonics quantum computers do exist, very much so. Um, like that's exactly what Xanadu is doing, is photonic based computing. So I don't know if that's like a different, if it's not on chip or something, but it's just weird that like I think photonics is like the third big player, because there's also teams in China that I know that are doing photonics computing. So I don't know why this is that way. Um, yeah, noise, obviously you can correct for some extent. You can actually fully correct. That's the whole point of error correcting codes. Yeah, crosstalk is hard. Okay, yes, controlling them is hard. I don't know what to say here. Like that's just true, but that's not like a problem. I mean, like that's a known problem with known solutions. So like, okay. And then there's algorithms, and this is something I really agree with, is that even if we had a fault tolerant quantum computer, what are we going to do with it? I think that needs a lot of work, and this is something I know Peter Shor has written about before. It's like, why are there so few algorithms? Is it because quantum computers aren't that good at things? Is it because making algorithms is really hard? Yeah, so I agree with this. We need more algorithms. That's very true. Um, Challenges are enormous. I agree, but that doesn't mean they can't be overcome. Everything, going to space was a huge challenge, and we did that. So it's not like we can't overcome these things. The largest quantum computers have somewhere between 50 and 100 qubits. I believe I saw that AWS just got a new neutral atom computer for 256. I know IBM has a 127 qubit system. So like these, it's definitely getting bigger. IBM says they want to make it to 1,000 next year. I think a bunch of companies actually have 1,000 next year as well. So like, probably get to 1,000 next year. I don't see why not. And two different approaches have been demonstrated with quantum advantage. I'm not sure where this came from, because there's been at least 4 experiments that I know of that were a quantum advantage. There was Google's 2019 paper. There was the 2021 paper from the Chinese team using photons. That was published in Science. Of course, I'll link these below. There was a superconducting qubit one also from a team in China, that was published in 2021, that used 56 qubits, I believe, or maybe 66, I forget. And then there was the most recent one that I know of, which is Xanadu's work, which was a photonics one that was 2022. So there's definitely at least 4, maybe more. I'm not super up to date on hardware that have been demonstrated. So I don't really know why 2. Maybe it's because it's only superconducting and photonics is what they mean. Like those are the 2 approaches. But it's weird though that if they're saying, okay, if they acknowledge photonics here, that they didn't mention it up here. But anyway, yeah, those are not super useful calculations. The record-breaking useful calculation is factorization of 21. I don't know why this is said either. It's not record-breaking. This paper was published in 2011. Like, how is it record-breaking? I'm pretty sure variational quantum factorization has also factored a lot larger numbers, so it's like a different type, but okay, yeah, like that's not, factoring 21 is not that impressive, but it was done like more than a decade ago. And it's weird that there's also some cute applications. Like everyone says these are the big applications, are chemistry and machine learning. People always say Shor's algorithm is like a ways away. So I don't know why these are categorized as cute and this is categorizing as record breaking. I assume quantum chemistry is not a cute application. I assume it's a useful calculation. Like I just don't understand this framing of it. Estimates say it's hundreds of thousands of millions, depending. I think tens of thousands is feasible for commercial relevance. And this is something where a lot of quantum computing enthusiasts claim that you'll get there more quickly because of Moore's law. I don't know where this comes from. I've never heard nor seen anybody say this, even the hype people and the investors and stuff. I've never heard anyone talk about this. I see a lot of people saying Moore's law is dead and quantum computing is the future, which may or may not be true. But I've never seen anyone say Moore's law will make quantum computers faster. That like I'm curious to see like what her sources are for like anyone saying this, because I'm serious. I've never heard anyone say this, and I agree. Like Moore's law will not make quantum computers faster. That's like no one should say that, but it doesn't make sense why this gets a whole paragraph. Um, Also, the problem with scaling computers isn't making ions smaller or wavelengths smaller. It's that's not the challenge here. Like even if we could miniaturize it, we don't need to. Like that's not the Moore's law that we would try to break. But yeah, so there's been some noise around NISC, which is something I actually have another video planned for, a really exciting one that I'll be talking more about NISC from a big picture perspective, probably 2 weeks from now. In which you just accept the noise. No one has found anything useful to do with them. I disagree and agree with this in the sense that I think they've been overhyped, and I'll talk about that more in another video. Um, there's something else. I have some other tabs open. I have some notes to say, but I don't know what else to say. We'll just get on with this. Then she says what other people have to say, and I have no idea who these people are. I looked at this person, Mikhail Diakonov. I'm sure I'm saying that wrong, but like I looked at their like why I don't know. I know a lot of people in quantum computing, so like why don't I know these people? And as far as I could tell, in the last like 8 years, when I looked at their Google Scholar, the only quantum computing work they've done was like this book. So I don't really know like what's going on. Like that doesn't really seem like they're actually that much in the field. Um, like no, we will never have a quantum computer. Like okay, by some definition, we already have a quantum computer. Like I you can say no, we won't have a useful quantum computer, but we have one, like a computing device that can do computations. Like we literally have those already. Like that's not disputable. Um, and we might have some special task quantum device operating at millikelvin. Like I guess they just don't like ions or photons, so I'm not sure what's up with that. Um, Also, the saga is a profound sociological analysis. Once again, of all the bubbles to say is a sociological analysis, like it's not even $1 billion. Like look at the housing bubble or the .com or AI winters or something. Like this is not a big bubble. It's not like profound. It's not a huge field. Like I don't get. It's almost like people are overhyping the hype in terms of its scale. Like this is still a niche area in terms of investments, which is just I don't know. That's just here's another one, law and policy, which they describe quantum winner. Sure, yeah, sure. Like it's important to understand that. And then another person, I don't know who this person is. Yeah, I don't know if it's going to solve global warming. Sure, this is a very reasonable take. Yeah, we haven't shown a ton of work right now. There's challenges in scaling up. That's pretty reasonable. Yeah, there's a lot of money going into these things. Like, there's nothing really to say here. These are all the points that I usually agree with. Is that like a tempered, reasonable perspective on it. Um, yeah, first of all, smaller startups will falter. I mean, that might be true. I don't know if startups are going to make it in quantum computing directly, but it's weird to say that. I might be totally wrong, of course. Maybe it'll work. I don't know. I'm guessing, but then present all of this as if you're definitely not guessing. Um, and then it's also weird to say that like there's these people. I don't know if they're so heads down in their own field. Like look at AI. Um, the, there were people working through the bubbles and look at AI bubbles and winters if you want to know how this is really going to play out if a winter comes. And that's all I'm going to say on that note. So I think it's just some weird statements here. So basically, yeah, I saw this from a Reddit post on the quantum computing subreddit, and it's just I don't think it's a very reasonable take on the quantum computing situation. I agree, like there's an overhype of quantum computing. I don't know if that means, but an overhype doesn't necessarily mean there's an over investment too. I want to emphasize that. People can say quantum computing is bigger than fire, which is not true. But at the same time, the monetary investment, okay, if something is bigger than fire, like hundreds of billions of dollars would be invested in. Like bigger than fire is like the biggest thing ever. So the money doesn't reflect the words that are being said. So using the words to say, oh, the money is going to change because of it doesn't really make sense, like from a fundamental logical perspective, because you're saying, okay, yeah, it's overhyped, but the money doesn't match the hype. Like so there, if it becomes underhyped, that doesn't mean the money will match the underhype either, or the winter. So I guess that's just the big point. Hopefully I made my points concise. I know I sort of just went through this randomly or just sort of line by line, but hopefully it's clear that I think they misrepresent the author of this misrepresents a lot of the what's going on in the field. I don't think they're doing it intentionally. I imagine they're just adjacent to the field, and so they look at what's going on on LinkedIn, right? And you see all this crazy stuff, and so you sort of they're overhyping, so you overreact to the overhype, and there's this whole thing going on there. But that's basically my thoughts on this and why I think this does not represent the state of quantum computing, and a lot of the points they make are misrepresented or don't really make sense when you consider a broader perspective. So yeah, that's hopefully it. I don't want to make a habit of responding to bad takes on quantum computing, because then I would never do anything else. There's so many. But this came from a sort of a scientific perspective and was hugely popular with hundreds of thousands of views. So I just want to make sure that like at least 100 people that watch this video don't end up with the wrong impression. Now don't make a mistake. I think a quantum winter might be coming. I don't disagree with the thesis, but I don't think their reasoning is up to par. So yeah, that's it. More normal content later. I just had to make this one.